Every single C919 flying in China today relies on a foreign propulsion system. Beijing did not build these engines. Instead, they are imported from a joint venture between the United States and France. This single critical component accounts for nearly 1/3 of the aircraft's total value. When Washington suspended export licenses for 5 weeks in 2025, Beijing's commercial aviation ambitions almost ground to a sudden halt. To break this choke point, Beijing developed its own domestic alternative. But a massive strategic gamble lies ahead. This experimental engine has only been flight tested once on a heavy military transport, without a civilian passenger. Yet China is ready to stake its entire civil aviation sector on it. Before we analyze this technological showdown, click the like button if you appreciate strategic aviation breakdowns. Your support keeps us going, so subscribe and join us for the rest of this geopolitical puzzle. What we uncover next will challenge your assumptions about global aerospace supremacy. Together, you and I are going to dissect the hard data behind this new propulsion system. We will expose the unpublicized test flights and map out the geopolitical timeline for this massive industrial gamble. Let's examine the aircraft at the center of this battle, the C919. This narrow-body jet is Beijing's direct challenger to Western duopoly standards like the Boeing 737 or the Airbus A320. And it is actively flying routes right now. 3 major state-owned carriers have integrated it, transporting millions of domestic passengers across Chinese airspace without a single safety incident to date. Developing, testing, and securing regulatory approval for this jet took decades of intense state planning, with engineers masterminding everything from the wings to the complex internal avionics wiring. From an industrial perspective, it is a major victory, proving that Beijing can successfully assemble a modern passenger jet on its own soil. Yet, a glaring strategic vulnerability remains at the center of this achievement. The crucial propulsion system lifting this jet into the air is entirely non-Chinese. Named the LEAP-1C, it is manufactured by a joint venture linking American and French aerospace giants, leaving the C919 completely dependent on Western supply chains. Physically, these turbofans function as massive intake systems, compressing air, igniting it with fuel, and generating the immense thrust required to propel the aircraft forward. While the physics are basic, the manufacturing complexity is extreme, which is why a tight global oligopoly controls this market. Western aerospace firms have spent over 50 years refining this technology, allowing them to capture nearly 30% of the entire commercial aircraft's production value. That means nearly 1/3 of this Chinese jet's value is manufactured overseas, controlled by foreign powers. Consequently, every single completed airframe flies with a foreign core, exposing Beijing to severe supply chain leverage. This critical vulnerability explains why Chinese planners have launched an aggressive, highly strategic push to secure true technological sovereignty. We will examine that effort shortly, but first, let us look at the geopolitical cost of this dependence. The leverage was pulled in July of 2025, triggering a crisis that shook China's aviation establishment. Washington suspended the export licenses for those LEAP engines. With a single administrative stroke, the United States disrupted manufacturing operations located thousands of miles away in Shanghai. American suppliers were legally blocked from delivering engines for 5 weeks, halting assembly lines and freezing C919 production. Deliveries stalled, disrupting state airline expansion plans and leaving newly scheduled flight routes without any actual aircraft to service them. Travelers had booked seats on uncompleted jets, while commercial leasing companies faced sudden, open-ended delivery delays. This foreign-dependent supply chain immediately seized up, resulting in only 32 aircraft deliveries being completed by the end of 2025. This fell far short of state industrial targets. Backlogged orders piled up because these highly advanced airframes could not be finalized without importing that one vital Western component. This supply shock sent a chilling warning to defense planners and industrial policymakers in Beijing. They realized that domestic manufacturing capacity matters very little if a geopolitical rival controls the propulsion technology, giving them ultimate veto power over your skies. Structural engineering and assembly mean nothing if the core engine is subject to foreign sanctions. This was a harsh lesson in geopolitical reality. While constructing wings and fuselages is manageable with capital, turbofans demand exotic metallurgy that survives temperatures exceeding 1,000 degrees Celsius, sub-millimeter precision machining, and decades of highly specialized institutional knowledge that most nations simply do not possess. Consequently, this high-barrier sector remains dominated by a Western cartel, leaving China completely shut out of the engine manufacturing club. This forced a critical strategic question. Could China achieve complete self-reliance? Could they engineer a safe passenger engine to eliminate this geopolitical vulnerability? This query brings us directly to Beijing's highly classified flagship project. Their strategic domestic answer is the CJ1000A turbofan, developed by the state-owned Aero Engine Corporation of China. Far from a rushed contingency plan, the design specifications target 28,200 pounds of thrust, projecting serious industrial intent. This massive power equals 14 heavy-duty pickup trucks pulling together at absolute maximum output, with an extended range variant pushing toward 29,500 pounds of thrust. This massive output practically matches their Western counterpart pound for pound, proving that Chinese military-industrial planners can match the raw capabilities of foreign imports. The hardware also shares identical physical dimensions, featuring a fan diameter of 1.95 meters and an overall length of 3.29 meters, roughly matching a standard utility vehicle. This direct spatial correlation with the LEAP engine is a calculated engineering decision. It ensures the new power plants can integrate directly into the existing airframe architectures. By relying on this drop-in compatibility, aerospace engineers can swap systems without redesigning the wing mounts, bypassing years of aerodynamic testing and billions in development costs. This strategic modularity saves billions of dollars and years of development, while the internal engineering details prove even more impressive upon closer inspection. The rotor uses 18 advanced hollow titanium blades, a design choice that drastically reduces weight while allowing faster rotation without structural failure under extreme pressures. Beyond the fan, they developed a complex 10-stage compressor containing 18 stacked rings of blades. This system aggressively compresses the intake air before it undergoes combustion, dramatically boosting the fuel efficiency to rival Western performance. This multi-stage compression ensures the air reaches optimal density before ignition. By packing high concentrations of oxygen into the combustion zone, the design ensures the engine burns fuel with maximum strategic efficiency. Within the combustor, 3 fuel nozzles are manufactured using advanced 3-dimensional printing, showcasing Beijing's rapid mastery of cutting-edge additive manufacturing on a global scale. Conventional manufacturing demands welding dozens of tiny metal components together. But 3D printing allows engineers to fabricate the entire nozzle as a single unit, eliminating structural vulnerabilities while maximizing thermal resilience under extreme conditions. We are not looking at legacy technology dusted off and rebranded. Instead, this is a highly sophisticated piece of sovereign engineering, backed by massive state capital. Yet a critical geopolitical question remains, one that ultimately determines whether this massive strategic gamble will actually pay off. Has it actually taken to the skies? Yes, but not on the civilian C919 jetliner. This propulsion system has already logged flight hours elsewhere. Its trials took place on the Y-20, a heavy military transport aircraft utilized as a high-altitude testbed for unproven engines long before civil aviation ever gets near them. Technicians mount the experimental engine onto one wing of the Y-20 while maintaining a flight-proven engine on the other. This setup lets them monitor real-world performance, speed, and thermal stress safely, avoiding any premature risk to commercial passengers. Should a malfunction occur, the transport aircraft safely recovers using its primary, proven power plant. This rigorous aerospace evaluation spans months or years, compiling thousands of hours of flight telemetry. Analysts scrutinize how the machinery handles extreme thermal shifts, takeoff dynamics, and long-term structural wear under constant operational cycles. Each sortie feeds data into a massive intelligence puzzle, determining when the propulsion tech is safe for commercial airspace. By March 2025, top executives at AC, including a former COMAC deputy general manager, asserted that performance metrics had shattered their optimistic internal projections. Let that sink in, because such bold rhetoric is rare from state-backed insiders, who typically weigh every word. They confirmed that flight trials on the C919 are imminent. While that signals rapid progress, the underlying industrial reality is far more complex than mainstream headlines suggest. There is a critical hurdle most analysts are ignoring. In the aerospace arena, flying and global certification are worlds apart. Successful test flights do not immediately translate into regulatory clearance for daily commercial service carrying paying passengers. How long will this transition actually take? To find out, you and I must look past the media hype and examine the rigid industrial timeline governing this geopolitical race. Domestic certification for the power plant is projected between 2027 and 2028. Active commercial deployment on the C919 might commence by 2028 or 2029. Furthermore, scaling up to high-volume mass production to equip entire fleets is highly unlikely before 2030. For context, initial projections slated this engine for service in 2020 or 2021. This represents a major strategic setback, not some minor logistical hiccup. This multi-year delay is standard in high-stakes aerospace engineering, where safety overrides speed. Yet it remains a serious bottleneck for policymakers aiming to quickly replace vital foreign components. The global certification regime is notoriously brutal. Regulators must verify performance under extreme atmospheric freezes, intense heat, bird ingestion tests, and rare emergency failures that the average commercial passenger never even considers. Every threshold must be exhaustively documented, replicated, and audited before international authorities grant approval. This explains why successful flights do not guarantee rapid market entry. Strategically, we must also confront a persistent technological gap that continues to divide China from its Western rivals. Facing the LEAP engine it aims to displace, experts view the CJ1000A as a conservative evolution. Its architectural core reflects design paradigms of the 1990s, rather than today's state-of-the-art ultra-efficient power plants. The critical metric here is the bypass ratio, measuring the volume of air routed around the core versus what passes directly through the combustion chamber. Higher ratios yield superior fuel economy, drastically lowering operating expenses for commercial airlines. While China's current engine operates at a 9-to-1 ratio, future iterations aim for 10 or 12-to-1. In contrast, the competing Western LEAP engine already dominates this high-efficiency bracket, leveraging decades of refinement and millions of operational flight hours globally. This does not doom the Chinese project. Rather, the challenge lies not in basic functionality, but in global competitiveness. The real challenge is matching an established Western monopoly that boasts a 15-year head start and millions of flight hours across global fleets. Before we analyze this further, let us consider a strategic question. Is 2027 to 2028 a realistic target for Beijing, or are they being overly optimistic? Share your assessment in the comments below. I am eager to read your analysis. This industrial timeline explains why China is pushing forward regardless of the cost. Let us look at the grand strategy driving this massive technological push. Achieving self-sufficiency in propulsion strips Washington and its allies of their primary chokehold over China's commercial aviation sector. Historically, advanced jet propulsion represents the absolute peak of industrial difficulty. It is far more complex than fabricating airframes or avionics, standing as the ultimate technological bottleneck in modern manufacturing. Beijing's newest five-year plan, spanning 2026 through 2030, explicitly outlines this objective. The state policy prioritizes expanding C919 output while accelerating the domestic engine program, elevating it far beyond a simple research initiative. This objective is now locked into national policy, backed by sovereign funding and strict deadlines. What does this mean for the global market? While official C919 orders exceed 1,000, close inspection reveals a closed ecosystem. Nearly all buyers are Chinese state carriers and domestic leasing firms. Foreign operators remain highly skeptical of adopting this new geopolitical player. Lacking Western regulatory certification and long-term operational data, global carriers refuse to risk their capital or reputation. Fleet acquisition involves billions of dollars, forcing commercial airlines to demand years of solid safety telemetry before they ever consider breaking ties with traditional Western suppliers. Successfully fielding a domestic engine alters the geopolitical calculus in two major ways, representing the core of Beijing's strategic bet. First, it eliminates vulnerability to foreign sanctions that can freeze supply chains instantly, a leverage point that stalled aircraft deliveries back in 2025. Global aviation markets despise structural risk, which this self-reliant propulsion system eliminates. Second, it bypasses Western regulatory blockades, unlocking export sales in developing regions where Beijing holds deep trade leverage and can bypass traditional certification processes. While lacking the prestige of North American or European routes, these emerging economies represent massive passenger volume and budget-conscious airlines seeking modern, competitive narrow-body alternatives. This expanding market share is the true strategic objective for Beijing. The goal is not to immediately displace Boeing and Airbus on premium Western routes like London or New York. Instead, it focuses on offering a fully sovereign, narrow-body alternative to challenge the Western duopoly in non-aligned markets. As you and I monitor this technological shift, we see it goes far beyond a single engine. Industrial breakthroughs in 3D printed alloys, advanced titanium blades, and thermal barrier coatings will inevitably spill over into military aviation. These manufacturing breakthroughs feed directly into Beijing's next strategic move, a massive wide-body jet, the C919, paired with a scaled-up domestic engine built on the hard lessons of this smaller program. Crucially, some of this turbine technology is already migrating into newer military propulsion systems, proving that Beijing's commercial breakthroughs quietly double as major national security assets. Every successful test run, redesigned blade, and developmental setback feeds directly into the database for Beijing's next-generation aircraft. We need to realize this is about much more than just one engine under a wing. This is the very framework for a completely self-reliant aerospace industry, engineered step by tedious step. And this engine represents the critical test of whether that grand strategy can scale up as planned. If you want to follow this geopolitical chess match, hit subscribe so you do not miss our next analysis. Be sure to activate notifications so you see the upload immediately. I would highly value your take in the comments below. Can China actually pull this off on schedule? Or will domestic tech roadblocks push their timeline well past 2030? Drop your thoughts below, and I will see you in our next brief.